and the topic is energy audit. The module topic is energy audit, but actually the content of the course is more toward building, okay, energy audit of building. It is authored by Tariq Al-Shamiri, professor somewhere in the UK, consultant. You can Google his name and you'll find out he's a professor in UK. You see, the topic is energy audit, a workbook for energy management building. I tried to get the soft copy, but I couldn't. Okay, but what I got is some highlight of the book that you can find in the Canvas. You can download it. Okay, but that's only probably 10-15% of the book content. Okay. Today, I will try to complete the whole thing about thermal comfort. Okay, so I split it into 4 parts. General introduction, then the main thing will most probably on the energy balance. Then some additional knowledge about thermal discomfort, what is it, and so on. Then finally, we got a few problems. I want you to prepare something like what? A piece of paper maybe to practice. And after the class today, I will submit the first part of the assignment. Okay, I'll prepare 3 assignments. So the first part I will upload it today. Okay, then. Well, first of all, why we study this thermal comfort? Remember that the energy audit we discussed in this subject is related to building, and as you know, the temperature, the surrounding in a building is highly important. Okay, so especially in Europe, okay, in Europe or in Western countries, where they have big gaps between the condition in the summer and in the winter. That's quite important. Okay, for us, we face problem with heat. I think tropical heat, high temperature, and high humidity. We'll discuss a bit about those parameters later on. Okay, so based on ISO 7737. What called as thermal comfort is the state of mind in which satisfaction is expressed with the thermal environment. So it's basically the feeling. Okay, I feel like I'm comfortable. Okay, that is why later on at the end when we discuss about thermal discomfort, so we use some kind of it's defined based on the survey, okay, based on somebody's opinion. Are you comfortable with this temperature, something like that? And we have to rate it from -3 to +2. Okay, so it's a state of mind. Okay, and then as you might think, it will be really depend on the situation. Yeah, evaluating how comfortable someone is complex. Depend on where. I mean, here. This guy doing skiing will say that temperature of -5 is very comfortable. Okay, while when you have your dinner somewhere inside the room, it's different temperature. So it's really different. Okay, so it's really a matter of many physical parameters. I will get back to this one. Many physical parameters. Not only the temperature, okay, and we have to evaluate it all together. Yeah, it's not only the temperature. Okay, there are other parameters. Okay, and it is highly affecting work efficiency. Okay, so that you notice that government building, office building, they always have this air conditioning. It affects the mood, it affect the work rate, it affect how you work. So that's become very important. Okay. So how to maintain this thermal comfort? Okay, it highly related to two condition. Okay, number one is the actual combination of skin temperature and body core temperature. Okay, that provides a sensation of thermal neutrality. We say it's not too hot, not too warm, not too cold. That's the thing. Okay, you have okay, it's relative to your body temperature. Your body temperature is constant, around 36 to 37, I think. That is our body temperature. And the combination with the skin temperature, what will be your skin temperature? Okay, we'll get to this one later on. Okay, and then the second thing, okay, you have a good combination. So you have an air condition that is comfortable, not too warm, not too cold for you. And then the second thing is it's related to the energy balance. Okay. It's related to energy balance of your body. Okay, we human, we produce energy by metabolism. Okay, so it's basically we digest the food that contain chemical energies. And then our metabolism system help us to convert that chemical energy into mechanical energy and energy that can be used to sustain our organ. Okay, so we produce energy. Okay, we use it to maintain our body. Okay, that is for maintenance, and then we use it for our mechanical movement and so on. And then lastly, heat loss. Okay, loss of energy to the environment. And we will analyze this one by one later on. Okay, these are the parameters that is believed to affect the thermal comfort. The air temperature, okay, radiant temperature. Air temperature is the temperature that we measure with thermometer, room temperature. Okay, next, relative air velocity. Why air velocity is important? It is like when you are sweating and then you have one with this, we call it a static air, and another one is with you have a blown air. There is something called as boundary layer. Okay, so for example, you have here, I put it here. This is your skin. This is your skin, and this is your okay surrounding. Yeah, so your skin temperature is around. Have you checked 37? Yeah, 37, and the surrounding is 25, for example. So the temperature, the temperature is not like this. It's not like this 37 goes down and goes to 25. So that is not, okay. If this is the case, we will feel cold, right? You will feel it's cold. Okay. When, for example, this is your body temperature, okay, and this is 37, and the temperature of the surrounding is 25. Okay, temperature at 25. If you can feel 25 directly to our skin, directly, you will feel cold. Okay, you'll get a hypothermia most likely. Okay, because our body, if you remember, we have a system and environment in. Sorry, when you study thermodynamics, so when you study thermodynamics, we have two space, yeah. One we call as I will draw it here. One we call as system. This is S. and the second one is surrounding. Okay, we always distinguish things as the two. One is the system, one is the surrounding. Okay, and then you can have a closed system. Okay, closed system means you don't allow energy to be transferred in and energy to be taken out. You also don't allow mass to come in and mass to goes out. Okay, that is one thing. An enclosed vessel with full insulation, for example. Okay, you have a room and then you close it all. You don't let air to go in and out fully. Then you have an insulation as such, no temperature change. That is a closed system. Okay, the opposite side is actually open system. Open system is you have a system and you allow the energy, the mass to come in and then to go out, and you also energy to come in and energy to go out. And this is our system. Okay, this is our body system. Our body system is open system. We eat. Okay, you bring mass to your system, and then we let it go as well. Okay, that is first thing. And when you sweat, basically you release a mass. Okay, through your skin. Okay, so you release the mass, and then with the mass you also release energy, go out. You do the activity, you release energy as well. Okay, you do work. This is thermodynamics. So, and then we can have different system. Okay, we can have system, we call it system that is adiabatic. Adiabatic means the system that is a closed system. You don't allow energy to go out. Okay, you don't allow energy to go out. So adiabatic means, for example, I'm in a room. I close every window all, so I will not let heat to go out and go in. And then inside the room, okay, I burn something. I burn something inside the room. So the room temperature will go up, okay, and the surrounding temperature will be constant because we don't let energy goes out and in. So that's an adiabatic. You are in a room, for example, you close all of the windows, you insulate it well. So, and then you use air conditioning. Okay, air conditioning, you can argue with me that is not adiabatic. No, when you cool it down, you take out energy and the temperature goes down. Okay, that is called adiabatic condition. Okay, there is one thing, condition as well. It's called an isothermic. Isothermic. This is our body system. Okay, we are an isothermic. Actually, part of our energy, part of our food that we consume, it is used to maintain the body temperature. Can anyone guess, or maybe you know, if you are, why the temperature is maintained at 37?
Because the biological
biological activities.
Yeah, the biological enzyme is optimal somewhere between 40 degrees.
Yeah, pandai. Okay, yes, that's the best answer. Yeah, yeah, we have to maintain that one because we want to support the enzymatic reactions. Enzymatic reaction is optimum at 37, and our body temperature is about 37. So what happens if, for example, you do a lot of exercise? You do a lot of exercise, actually you produce a lot of heat. Okay, you produce a lot of heat and your body tries to release the heat out. You feel this is hot. So the releasing energy out is through sweating. So water is also the product of the metabolic reaction. High temperature of water and water evaporation. So sweat evaporation is actually the way to release the energy from our body. Okay. Okay, that's the thing. And yeah, we discussed two important parameters, which is the temperature and relative humidity that answer the thermal comfort. Okay, another thing apart from this physical condition is activity level. Okay, activity level related to your rate of metabolism. Okay, when you run, you need a lot of energy. You pump your heart beat faster. Okay, your heart beat faster. Your blood circulated faster. Why? We need to deliver the food to the cell. Okay. Clothing is an insulation to our body. So when we cover our body, basically the transport of heat into and out from our body is affected, and we'll discuss about this one later on. Gender, men produce more energy. This is not racist. I keep thinking about this one. I think it's related to the muscle density. Yeah. This is very sensitive things. Okay. Normally, women doesn't like it. And you ask their weight. Okay. Yeah. Some must don't ask your girlfriend. Yeah. You ask the weight, and you feel like the size, the volume, is more or less the same between a man and a woman. But then you will realize that actually the weight is probably 5-10% different because of the density of the muscle, I think, and bones, probably. Yeah. Age, of course, yeah, age. Then it's related to the size. Gender, that is, but that is not universal. It's supposed to be case by case basis. The same thing. Thermal comfort is case by case basis, but we can always find a common ground. Like, for example, the best temperature, ambient temperature is around 18 to 24, more or less. Okay. With relative humidity, not too wet, not too dry. So it's around 50 to 70, the ideal. Okay. So what happens if the temperature doesn't meet the normal condition? So the 37 is around a normal body temperature. Okay. So what happens is 40.5. It's called heat stroke. When after you get your vaccination, maybe you get heat stroke. But 40.5 is too high. You need to go medical assistance. 38, 39, below 40. That you can still handle, but 40 and above, that's big things. Tissue damage, 42. This is the fact. Yeah, this is an empirical fact. But I always think that the increase in temperature is actually to speed up the reaction. Yeah, that is my personal opinion. This one is just fact, but my personal opinion is. We need to, so it's like when you are in pain, the only explanation you are pain is that you're trying to recover. Yeah, that's the thing. Okay, 35, hypothermia. Hypothermia is the temperature below these things. And then when you have temperature of 32, this one is already damaged. Further cooling is unconscious. So this is the temperature condition. Yeah. Make sure you calibrate your temperature, your thermometer, yeah, all the time. I explained something about isothermic. So our body is isothermic. So I want to continue this discussion. So you have a body temperature here, okay, 37, for example. And you have ambient temperature is 25. This ambient temperature. This is 37 is your body temperature. The temperature of our body is 37. What we felt is not this. Okay. What we felt, okay, although the ambient temperature is 25, what we felt is not 25. If we felt it's 25, probably we will immediately go to the hypothermia. Okay. You see, there's a big difference. This is plus 12 degrees Celsius difference between your body temperature and your surrounding. Means that you will pump a lot of heat out. Okay, Q equal to heat equal to some constant delta T. So the higher the delta T, the temperature difference, the more heat you will release, you will go out. Okay, this is the reason why. Okay, you can try this one. You experiment. You play in water in a swimming pool for half 1 hour, 1 hour, 2 hours. You will feel hungry very fast, because what, you have to pump a lot of heat to overcome this temperature difference. Your body temperature is 37 and the water temperature is 25. Okay, this big temperature difference will force your body to burn more food, more ATP, so that you can maintain the 37 degrees Celsius. Otherwise, your temperature will go down, and you will have the hypothermia. Okay. Another condition is that, so what happened is that actually the temperature is like this. So it's like this. It's like this. So we don't feel the 25 here. We probably feel here 30, 32. Yeah, we will have equation to calculate this one. That's one. We don't feel the 25. So we feel way much higher than 25. Okay. Otherwise, if we feel direct 25, so now you will have a delta T not plus 12, but probably plus but probably plus 4 plus 5, which is good enough. Okay, plus 4 plus 5, which is good enough. Yeah. So this one is called as film theory. So there's kind of a static air, okay, very close to your skin, probably a millimeter thin, but it's static. When it's static, the temperature is very close to the temperature of our skin. If there is no film, for example, you swim, okay, you are in the swimming pool, temperature is 25, basically that film is not there. And then the conductivity of water is much higher than the air. So basically you have to produce a lot of energy to maintain the body temperature. This is the reason why if you go swimming in the river, cold water especially, you feel hungry very fast because of the high rate of metabolism to maintain the body temperature. Okay, yeah? Okay, I think we have enough preparation to go for a little bit of calculation. So the way to analyze our body temperature is by looking into the energy balance. Okay, energy balance of human body. We produce energy through metabolic activities. So basically we burn food. Okay, we oxidize the food. So through metabolism, you bring it to ATP, then you consume ATP to produce carbon dioxide and water, and then you need oxygen and so on. Okay, that's beyond the scope of this study, but you know it from your A level or O level. Okay, so we use so we use the metabolic energy for mechanical activities. Okay, this is for work, mechanical work, and then some of it will be released through this called as, I think, latent heat. Through the sensible heat and through latent heat. Okay, what are they? We will discuss later on. Try to pay attention to this. Okay, this is a normal energy balance. Okay. So we will discuss one by one, M, W, Q, S, Q, L. You please pay attention. Because the thing is, I use previous slide. Then when I tried to do the exercise, I couldn't do it. So I had to read the books again and then find out the full explanation. I think I provided complete information now. So if you follow me carefully, you'll be able to do this one. This is really fun. If you later on interested in doing the exercise and you want to do the balance of the, you want to calculate how much energy going, how much heat you produce, it's quite handy. The book is quite handy to follow. Yeah. So let's look into the metabolism. So metabolism is basically this is God. Okay, it's basically this rahmat dari Tuhan, God's blessing. Yeah, we produce metabolism according to the need. Okay, when we rest, we produce probably less. When we do exercise, you produce more. When you think and when you are attending lectures like this one, probably you produce a little bit more if you use your brain well. Okay, our brain cell is the cell that utilize most of the energy in our body. Okay, so according to the need. Okay, you see somebody probably doing nothing but think a lot. Most likely will burn fat. But to my surprise, there is no therapy of diet by thinking. No therapy of diet by thinking. I was wondering, energy balance is not only body exercise. If you want to burn, you can think. You can, I don't know, but one thing is in the tradition, stress. Yeah, I don't know, in my kampung, stress is associated with being skinny. So stressful people, sick people, they tend to be skinny, or without even doing exercise and with eating a lot. Eating a lot, stressful, you can be skinny, but yeah, but we know that some people channel stress, I don't know, by eating a lot and building up the muscle and the fat, some. But all must follow the energy balance, okay? The what you generate, the same as what you use and what you release, balance. So this is a handy number, okay? And many of the equation that I will explain to you, it's an empirical equation, yeah. So don't worry if you don't remember the equation. I will give it all to you. I will give them all to you. No need to memorize. You just try to understand. Okay. The rate of metabolism. Okay, this is based on empirical measurement. Is between 46 and 174, and the unit is watt per square meter. Yeah. So square meter here is this is what is joule per second. Per square meter is the surface area of human body. Okay, and okay, you want remember this well. So 46, 174. So people make it a little bit easier by using different unit, which is MET. So 1 MET equal to 58 watt per square meter. So when you do, when you relax, when you sit relaxed on your sofa, for example, without thinking heavily about exam or assignment, you just enjoy watching movie. That is about 1 MET. 1 MET is 48 watt per square meter. These are some of the graphical information about how much energy you spend. You're sleeping about 0.8 MET. See here, enjoying yourself on a sofa, watching TV or K-drama. Okay, yeah, you spend about 1 MET. Then you go walk, exercise in the park. It's about 1.2 MET. Easy to remember. If you run, that's about jog. If you go jog, okay, that's about 2 MET. And if you do heavy exercise like badminton, squash, that's about 3 MET. So much easier to remember than what the exact number of that. Okay, 1 MET. Yeah, again, 1 MET equals 58 watt per meter square. Okay, so of course, then this rate is average. and then depend on a lot of parameters, your properties, your body, your height, your weight, the activities you do, and so on, and then age as well. So older people, okay, and older people and children, they got a lower metabolism rate, about 78%, and women got about 15% less of men metabolism. Okay, this fact, I want you to. So the way to master this subject is you go through the slide and just read, because I think it's self-explanatory, so it doesn't need in-depth explanation. So these are some of the basic information. So metabolism, okay, this one it's very hard to calculate. It's very hard to calculate, so we use empirical data. So these are the metabolism rate for various activities. So no worry, don't try even to memorize this one. I just want you to know this one, 58. Okay, I'll give it to you. Okay, of course this is guessing. Standing medium, standing light, what is the difference? I don't know exactly. I mean, this is from the book. So it involves a lot of guessing. So when you do work, heavy works here, probably lifting something, you carrying something, then it's around 140. But you do this is strenuous work like sport. I think it's like sport. That is 174. So in the end, you'll need to guess, okay, and the accuracy of your guessing will affect your calculation later on. Okay, so we completed the M on the left side of the balance equation. Then now we'll go to the right side of the equation. We go to work, okay. So work is energy that is consumed by our internal organ. Yeah, your heart, your lungs, okay, breathe in and breathe out the things, your hand to work, your mouth to speak, your eyes to see, those all consume energy. Yeah, all consume energy, and their energy consumption is around all of those. Yeah, so basically if you don't do anything, this 50, so this 1 MET, okay, this 1 MET is basically to maintain our body, yeah, to maintain our cell alive. So we need 1 metabolism, 1.0 MET. That is for your lung to pump, so your heart to pump, your lung to expand and constrict. What else? Your eyes to see, your ears to listen, all of this. Your brain to think. Not very hard, just small thinking. Those are 1 MET basically. Yeah. So the way to estimate the physical work is we use a fraction of the things. So we use the mu. Mu here is basically the efficiency. So basically we just calculated based on probably less than 20% of the metabolism, because if I rewrite the equation, it's become W equal to mu times M. Okay, so the maximum of the mu we take for physical work is around 20% maximum. So 0 is when you don't move, so we don't do anything. Okay, that's so basically this one. So if you want to estimate, for example, how much is energy per area of your skin when you walk, then you have to estimate from the total metabolism energy of walking. Well, say it's around this probably, and then you just estimate 10%. So it's 9.28. That is for walk. So there is no exact science, because it's almost impossible to do it. Okay, but try to come up with a sensible estimation here based on the guides provided here, based on the table, based on this value. Okay, so now we want to look into energy balance. We know what is M over A, we know what is work over A, okay? And next we want to know what will be the Q loss, heat loss. Okay, QL and QS here, it's represent the latent or wet heat loss, and QS is sensible or dry heat loss. Okay, that's per unit area. That's already, so basically that is a big Q over A. Big Q over A equal to small q. So this is per area of the body. Okay. Okay. So what important you to know is that the average, okay, the average mean body surface area of an adult human is around 1.77. You can argue with me, European is bigger. The Dutch people are very tall. Melayu is relatively small. Okay lah. Yeah, more or less. This is average. Okay, you need to take into account that one as well. Okay, this is the basis of energy balance. So now how to calculate one by one. Okay, first, latent or wet heat. Okay, latent or wet heat. Okay, QL. It consists of three components. Heat that is diffused through the skin. So this is QD. Heat that is gone through the evaporation of sweat, QE, and then heat that is lost due to respiration. Okay, I'll get back to this one later on. So remember the three components, QD, QE, QRS. So we'll do it one by one. So QD, okay, it is not controlled by a thermoregulatory system whatsoever. It's just flowing. Okay, it's nothing. And then this equation is empirical. So empirical is based on data, yeah, based on fitting the curve. Okay, you have a lot of data and you try to develop the equation. And you put some parameter there. You come why this number, sir? Well, this comes through the curve fitting. Okay, why this number? Why this number? Okay, this come through curve fitting. But what we know is that the heat diffusion is affected by two things, TS, okay, or TdB here. TS is actually, TS is the skin temperature, okay, and PS is water vapor pressure on the top of your skin. Okay, and TA or TD, sometimes I write it TA. So this is the ambient temperature, yeah. This is the ambient temperature. So, if you know somebody's temperature, if you know somebody's weight and metabolism, the activities, you know what activities, what they are doing. So basic work is basically based on the activity. Metabolism and based on the activity. And then we can guess also work, we can estimate what will be the temperature of the skin temperature. Okay, so what will be the pressure of the air on the surface of the skin? Well, it's also empirical equation. So here, theta here, what is the name in Greek here? Okay, I call it theta lah. It's a relative humidity, so it's given in fraction, not 50%, 10%. So it's just zero. When it's 50%, you write it 0.5. When it's 70%, it's 0.7. So it's a relative humidity times a constant. This is a constant times exponent of 17.27 times TdB. This is TdB is ambient. So dB is dry bulb temperature. Dry bulb temperature is ambient temperature, the one you measure with temperature. The one you measure with thermometer, yeah, that is TdB. TS is most likely the temperature that you measure using the thermometer when you go somewhere, when you try to enter the premise. I think that would be TS. No, that will be temperature nearby the skin. Yeah. So that's relative humidity. So if we know, so you can estimate all of those. So next we go to QE. Okay, this is heat loss due to the evaporation. So this one also empirical. So it's 0.42. That is a constant. This also constant. So how do you get this one? It's from data, fitting of the data. Okay, if you are interested in fitting of the data, I can always. So it's like when you do regression. Okay, when you do regression, you have parameter, then you find what is the constant. Okay, and lastly, the Q respiration. Okay, it's happened because of you inhale the air. Air has the temperature of ambient temperature, for example, 25, and then it's enter your lung. Inside your lung, you have you are hot, you are 37. Okay, so some of the heat then transfer to the air in your lung. And when you exhale, now the temperature of the air leaving from our nose increase from 25 to more or less 34 degrees Celsius. So you see that there is heat that is released. This is why, for example, you are in a snowy region, or in further north of the globe, when the temperature is very low, you inhale air at temperature of -1, for example, and then your body temperature is around 37. You see the lot 37-degree difference between that. Maybe the air temperature is the exhale air temperature is not 34 in that case, but what I'm very sure is that you lost more energy when you are in a very cold temperature than when you are in the normal temperature. So that's the thing, and the equation is also empirical. TB here is temperature of dry bulb. This is the ambient temperature. M is the metabolism rate. M. TS is a water vapor pressure. Okay, water vapor pressure here on the skin. Okay, so no need to remember all of this equation. I'll give it to you for test or for exam. Even I don't remember, so how can I expect you to remember? Okay, that is okay. If you look into the equation, we are done with QL. Okay, and next we'll go to the QS. Okay, sensible heat or QS. What is that? It goes through. Okay, you have heat here. You have a heat produced from the metabolic reaction. So the heat, okay, transport through the surface of your skin. So this is your skin surface. Yeah, through conduction, because there is no way you can. There is nothing flowing outside. Okay, so go conduction, and then from the skin, so it goes through convection because of the air blowing, and through radiation. Radiation is the radiation heat transfer because of different temperature. We don't need any medium. It just emit the photon. You are when your body temperature is higher than your surrounding, you're radiating the room. Yeah. So of course it's not like a nuclear radiation. You emit photon through the surrounding. That's called radiation. Okay. So based on this mechanism, so what we know is that we can use this one to measure. Okay, this part. We can calculate QS just only on the conduction, or we can measure it by estimating the rate of convection and the rate of radiation. So either the two approach will be okay. Conduction, you can calculate what is the heat, the rate of heat transported during the conduction. This is supposed to be equal than what you have in convection and radiation, because we don't accumulate heat on the surface of our skin, as you know. Okay, that's the thing. So another aspect of convection is that we human, we have clothing. Okay, clothing act as insulator. So by wearing clothes, we actually reduce the rate of heat transport from our body to the surrounding. Okay, clothing act as insulator. That's the thing. There is some of the empirical data on clothing. Okay, and there is a unit called one CLO, which is equal to this value, 0.155 meters square degrees Celsius per watt. Okay, this value is derived from, I will come back to this one later on. So when of course, when clothing is really hard because everyone wearing clothes differently. So there are a lot of guessing in it. Okay, when you put the parameters, but what important is that you need to realize, you need to consider the effect of clothing. Okay, when you estimate the heat loss through the sensible heat. So let's go. So the first one is through conduction alone. So the equation is Q conduction equal to EC is area of the clothing divided by the A is total area of the body. K is a constant. X is the thickness of the skin. Okay, and TS is of course the temperature of surface, and TCL is temperature of your cloth. So the inner part of the cloth. Okay, and then you can get that one. But actually, we can simplify this equation because X, we can measure X. This equation is impractical. So we have a more practical equation. Q is equal to TS, TCL. So it's basically the same thing here. All of this, okay, all of this was simplified into this. Okay, we have a constant here, 0.155. And we have some empirical value that we can get from a table. I'll get back to the table later on. Okay, so what is TCL? What is the temperature of the cloth? We use this empirical equation. It's a function of what are you doing, the metabolism rate, and then the mechanical work you do. Are you walking? Are you what activities and your mechanical work, and then ICL. Okay, ICL here is given through the table, and then we have a PS. It's a pressure of water on top of your skin, and then a TDB is the ambient temperature. So you can calculate sensible heat using this one only, or you can calculate it by, okay, and then the clothing factor, okay, is related to the CLO. Okay, this is the equation, and CLO is given. This is empirical data as shown here. Okay, so this is the empirical data as. Okay, next we do convection. So if you cannot calculate this one through conduction, you can calculate it through convection and radiation. So convection is very simple. So this is the heat of convection is a constant. Okay, this is the driving force. It's always mass transfer is always something as a constant times the driving force. The driving force is the difference between your clothing temperature and the ambient temperature. Okay, so FCL is a factor that incorporate the role of the clothing. Okay. So let's see how we, so the convection coefficient can be estimated using this. Okay, and then there are two types of convection. Okay, for example, you have a coffee. every morning I drink coffee, and then it's too hot, for example, and then what you do is you just let it be, let it cool over time. Okay, you don't do anything. Okay, this called as free convection. Okay, I repeat again, this called as free convection. You are sitting in a room, idle, not doing nothing, and then some of the heat will be released from your body through convection, and this convection called as free convection. But when you walk, for example, when you walk, okay, that is basically you apply something. There is a speed of the air, okay, here, speed of the air around your body, okay. Okay, this called force convection. You do something, okay. For example, now you have a cup of tea, it's too hot, and then you blow air. You blow air on its surface. Oof, okay, I don't think it's not sunnah here. You blow it. Then you have force convection. So you have two different types of coefficient of convection, yeah, free convection and force convection. Okay, we get this one, HC. Now FCL. FCL is cloth factor. So it's given from the empirical equation. It's really depend on the ICL, yeah. You look into the ICL, then you can estimate what is the FCL. Simple. So this is the clothing factor. You got the CLO in this unit, and you have the one in this unit. So we need this coefficient to be able to solve the convection and I think conduction. We use this ICL, the CLO. Okay. Next, the sensible heat, I repeat again, released through conduction. You can calculate from the conduction or through convection plus radiation. So you got this convection. Then next is radiation. Radiation through a body. It's very simple. It's the heat of radiation, the rate of our body emitting heat, emitting photon is equal to, there's a constant, radiation constant. Okay, the value is 6 watt per square meter Kelvin. Okay, and it's a temperature of the cloth minus temperature of ambient. Okay, that's very simple here. That's it. So I'll make a summary. Okay, you look into this carefully. So we have 4 parameters. The metabolism equal to work plus QL plus QS. Of course, this one, okay, in this equation, M here is absolute M. So you need to make it an M over A. Okay, and this is W over A. If you want to use the watt per square meter, and this one become the small q, QL, and this is a QS. Yeah, be very careful. The best way is to check the unit all the time. So I'll just do a quick summary. So M is empirical data. It's given in the table. Yeah? So depend on what activity you do. Work, okay, the work is depend on the mechanical activities you do. You're walking, you are sitting, and so on. You're doing exercise. And it is normally taken from some fraction of the metabolic rate. And it's from 0 to 20%. 0 to 20%. But the thing is, I think this is, I don't know. If you notice there is something strange about this fact, I'll give you bonus point. Because something is that's not consistent with the previous slide. Okay, usually below 20, and it's 0 when motionless. So when you idle. Okay, this is very simple. M from table, power output just from fraction, and you just guess. Okay, you do the heaviest exercise, give it 20%. Okay, give it 20%. You are running, you are playing badminton, you are sprinting, 20%. Okay, so now let's go one by one with QL and QS. QL, okay, QL is from diffusion, evaporation, and respiration. Yeah, QD is given empirically, this equation. It's a function of TS. TS is given here. TS is empirical equation is a function of M and W, easy. Then it's also QD, also function of PS. PS, okay, PS given as an, this is the water pressure on the surface of the skin. It's a function of relative humidity, okay. And the ambient temperature. Okay, next QE. QE is function of weight and, function of work and metabolism rate, simple. And then respiration, okay, QR given as the also empirical equation is function of metabolism, ambient temperature or dry bulb temperature, and the pressure. Okay, that's QL. Okay, remember there are two type of QL. Yeah, Q with capital Q, that give basically you have to multiply it by the surface area of the body, and then the small q is per square meter body area. Okay, and then the second energy loss is through sensible QS. QS can be calculated in two means. You can calculate it simply by using the conduction key, small key S as well here. Okay, QS through conduction. So we have an equation of QS equal to this one. Okay, and then the clothing index here we get it from summary table. This is the empirical value. MT, temperature of clothing, we can estimate it from the mass, from the metabolism rate, weight, ICL, temperature of ambience, and the pressure of water. Yeah, panjang ini ya. Okay, you can calculate that one. If you don't like it or your data is insufficient to calculate that one, you can calculate the QS from convection of and radiation. So it's from this one, convection and radiation. So we get this convection equal to the convection constant, clothing factor times delta temperature. And then HC is really depend on the condition, can be free convection or forced convection. Forced convection is when the air blow to you or when you walk, either of this, the relative velocity of the air. Okay, because you can, for example, walk at the speed of 1 meter per second, and then you have the air facing, the wind blowing on the opposite direction at 1 meter per second. So the total VA then become 2 meter per second. Okay, I repeat again. It is not it's the air velocity, but when your body air velocity can also happen because of you move your body. Okay, and you have to take into account your movement and your air movement as well. And then FCL is given from the clothing factor is given from the empirical equation. So this is for the convection, and finally for radiation is equal to radiation constants times the difference of the temperature between the cloth and the ambient. T clothing you can calculate using this equation. Okay, there's a lot of calculation, and I can tell you that I will put this kind of exercise in the final exam. So you pay attention to this one. Up to this point, any questions? I record this video, so some of the information I probably don't type. You can recall it back from watching the recording. Up to this point, do you have any questions?
No question. Just process.
Okay, let me see. What time is it? Okay, a little bit more. I got a little more. I don't know how many materials yet. Okay, so we go to the thermal discomfort. Here, it's just additional information about the things. Thermal discomfort is predicted through something because remember it's a mind, it's a perception, it's the feeling. So we use a semi quantitative indicator. Okay, we get the information from the survey and the final data called as PMV, predicted mean food index. Okay, so you can have +3 for when someone feels very hot, +2 warm, slightly warm, neutral, 0, -1 slightly cold, -2 cold, 3 -3 very cold. Okay, that's the index. Okay, and then if you put this index, okay, then we can have a predicted percentage of dissatisfied, which is PPD. Okay, PPD you can have range from these things, and we scale it when. Okay, and then this one, of course, Z. Sorry, what was it? So basically, this information is telling you that feeling comfortable or not comfortable is relative, yeah. And then we got the information from the food. Some of the things, even when you have okay, somebody says this one is overall comfort, but then you can also have what we call as local discomfort. So what is this? So when you feel uncomfortable because of part of your body, okay, is uncomfortable. Okay, so for example, your feet is too cold, or something else. We'll discuss this one later on. So if you want to make the situation become comfortable, we have to amend the condition. What make that local discomfort? Okay, so we say the environment is comfortable when the food here is neutral. Okay, and don't feel any local discomfort. Okay, so therefore categories on local thermal discomfort. First one is convective cooling of body caused by drought. You are opening, for example, a car window. You feel not comfortable, might be, or I don't know. You open the oven when you bake a cake. You open it and you feel the heat coming. So that one you don't feel comfortable only on your face, probably. Yeah. So this is categorized as local thermal discomfort. Okay, you can also feel discomfort when part of your body is cold or heat. For example, here there is an illustration of a man hitting the hand. The hand is probably too hot. Okay, so this is called also radiation asymmetry. When you, for example, walk under the sun and you feel, you try to cover your face because your face is very sensitive to the heat. That's one thing. And that's the part that makes you uncomfortable because of you have to face the sun. Okay, you can experience local discomfort because of high particle temperature, hot on the top, cold on the bottom. Or you can also experience these things, cold feet, because of the uncomfortable temperature of the floor. Okay, I got 2 more slides. 10 minutes. Okay, so last part to discuss is floor temperature. Okay, it's happened to the direct contact of the feet and the floor. Okay, feet and the floor, and then it can, yeah, you feel discomfort because of the temperature is too hot or too low. Yeah. Okay. So that's interesting here that the heat that lost that causes discomfort. So when you step on the very cold surface, so you have a high temperature difference between your body and the surface temperature. A lot of heat goes out. That is actually that make you feel discomfort. Okay, and then the heat loss depend on many. Okay, depend on many. Other than floor temperature, you can depend on the conductivity, the heat capacity of the material, and so on. So there are many. Yeah. So if someone use footwear, it means that you have clothing factors. So the floor material is less significant. Okay, and then you see here. Based on the ISO 7730, so the standard set of comfort level at sedentary activity to 10% dissatisfied. Okay, that is okay. So that is here. So only 10% feel dissatisfied. So meaning that the temperature of the floor is around 20 to something, 19 to 29. So this range is range of comfortable floor temperature. Okay, it's really, this is some detail. So it's really depend. For example, in bathroom, the optimum temperature is 29 for marble floor and 26 for hardwood.